So in this video we're going to continue question 225, which is asking you to look at this resonance pattern of having an allylic lone pair and drawing an appropriate resonance structure for it. So we've worked up to G, and with G we see our first biological molecule with resonance. Or we should check, does it have resonance? And so what you'd want to do is to draw in the lone pairs. That'll help you see if you have any of the resonance patterns. Now, a carbon will only have a lone pair if it has a negative charge, and none of the carbons in this molecule have a negative charge. So the only thing that could have a lone pair are the heteroatoms, the atoms different from carbon, so oxygen or nitrogen. Each of those need to have 8 electrons around them. This oxygen at the top left already has 4, 2 in each bond, so it needs 6, 8, 2 lone pairs. This oxygen in the middle has 1, 2 bonds. That means it has 4 electrons, 2 in each. So you need 6, 8, so 2 lone pairs on that one. This nitrogen on the right side, that one has 2, 4, 6, 8 electrons around it already, and so it doesn't need any lone pairs. Alright, so those are all our lone pairs. Now we do have lone pairs in this molecule. Are they allylic lone pairs? Well, first of all, those are not. Why? Because they are on an atom in a double bond. Allylic means you're one atom away from an atom in a double bond. So those are not allylic lone pairs. But these here are allylic lone pairs because those are one atom away from an atom in a double bond. So we do have allylic lone pairs, and that means that acetylcholine has resonance. So we want to warn the world, acetylcholine doesn't actually look like this. It looks like the average of that in a different structure, another structure, that we want to add and average together. And so we have those big loud signs, the brackets, that are telling people, watch out. The structure here isn't the correct one is the average of all the structures in the brackets. So we have the allylic lone pair, and you would want to remember the curved arrow patterns that go with it. The allylic lone pair always goes to the bond that connects it to the double bond. And the electrons in the double bond, those electrons always go on the atom in the double bond further away from the lone pair, the allylic lone pair. So to draw the resonance structure, just copy that molecule exactly as it is. Just without the curved arrows. And now we want to look at which atoms the curved arrows are affecting, because the formal charge on those atoms may change. And sometimes it's easier to calculate the formal charge on a carbon if you have the hydrogens on it drawn explicitly. So we only have one carbon here. Excuse me, the carbon has a 0 formal charge, and so it needs 4 bonds, and 1, 2, 3, 4 bonds are already drawn. So that doesn't have a hydrogen. So we don't need to worry about drawing hydrogens in our new molecule. All right, now we can think about those curved arrows and how the electrons are moving. Let's start at the bottom. Wherever you have the tail, whatever is next to the tail of a curved arrow, those electrons are moving away from that place, so you erase them. Wherever you have the head of a curved arrow, that's where electrons are going, so you want to draw them in. If the head of the curved arrow points at a bond, then you draw in another bond. Wherever you have the tail of a curved arrow, those electrons are moving, and so you want to erase those electrons. Wherever you have the head of a curved arrow, wherever that's pointing, that's where electrons are arriving, and so you want to draw in electrons. If the head of a curved arrow is pointing at an atom, then you draw in the electrons as a lone pair. All right, now we just want to go through this and calculate the formal charges. So this oxygen here, oxygen is in group 6A minus, it has 6 dots. This oxygen has 6 dots around it and 1 line, so that's 6 minus 7, negative 1. So that has a negative 1 charge on it, that oxygen. Okay. How about the carbon? This carbon here. Electrons moved around that. Maybe the formal charge on that changed. Well, carbon's in 4A, group 4A, and you subtract 0 dots, and there are 4 lines around that carbon. And so that has a 0 formal charge. How about this oxygen? 6A, group 6A, minus, it has 2 dots and 3 lines, 1, 2, 3. So that's 2 plus 3, 6 minus 5, that's a positive 1 charge. And so that oxygen is going to have a positive 1 charge, or I should just say positive 1 charge. All right, and so the true structure of acetylcholine is not the one on the left, it's not the one on the right, it is something in between. And so let me draw it out, just a little sketch, so you get an idea of what these resonance structures are trying to communicate. So that would be somewhat what that molecule would look like. You'd have these bonds here somewhere in between, a single and a double, right? Not a double, not a single, but something in between. Not a single, not a double, but something in between. And the charges on the atoms will be something in between a full charge and 0, like in the structures. So that would be acetylcholine. And so you can see the significance of this. Remember, resonance has a meaning. The significance of it is that the more resonance you have, the more stable the molecule is, and also the more rigid it is. And you can see why in this drawing. First, it's more rigid because if you just looked at this molecule, you'd think this single bond could rotate. But now that you see the resonance structure, you see that there's part of a double bond there. There's part of a pi bond there. And so pi bonds can't rotate. And so that bond actually can't rotate. That makes the molecule more rigid. And second, the molecule is really stable because the charge is spread out. These electrons are not just stuck on individual atoms. They're spread out over multiple atoms. Charge is a sort of burden for atoms. Charges repel each other, and they make things want to stick together. They make their atoms reactive. So it's a sort of burden. And just like if you had a monetary burden, a money burden, so you had to pay $5,000, if it was just one person who had to pay the $5,000, it'd be really difficult for that person to pay the $5,000. But if you spread that out and you had 100 people pay the $5,000, it'd be a much smaller amount. It'd be easier for those people to handle paying that. And similarly, when a charge is just stuck on one atom, only one atom has to bear it, and it gets really reactive. But when you spread the charge out, in each individual place there's less charge, and so the molecule can bear it better. So this resonance makes this molecule more stable and more rigid, and those are beautiful qualities in a messenger molecule. If a molecule is stable, then it won't react with anything as it goes from one place to another. And if it's rigid, then it'll reliably fit into an enzyme pocket. All right, last example for this in exercise 225, we have this structure. Let's draw in the lone pairs. And actually, I might just copy this structure down and expand a couple of these bonds. So this is a drug that's used in the therapy and diagnosis of tumors in your liver. Hepatic means in your liver. And so here, I'm just going to expand these bonds. This NH2 really means that nitrogen is bonded to 2 hydrogens. And then we'll have this zigzag, and this hydrogen here, that oxygen to hydrogen, there's a bond there between those two. So I just expanded those so we can calculate formal charge and see things a little better. All right, now let's put the lone pairs on this. So there are no carbons with a negative charge here, so none of the carbons have any lone pairs. We have to look at the heteroatoms, though. The atoms different from carbon, so nitrogen and oxygen. These need a total of 8 electrons around them. Now this nitrogen at the left has 2, 4, 6 electrons already, so we just have to add 1 lone pair, so it has a total of 8. This oxygen has 2, 4 drawn already, so we just have to add 6, 8, 2 lone pairs, on that oxygen. That oxygen toward the right has 2, 4 electrons. So we need 6, 8. And this oxygen here has 2, 4 electrons drawn already. So we add in 6 and 8. Okay, now that we have the lone pairs drawn in, we can recognize resonance patterns more easily. Let's look at these one by one and see if they are allylic lone pairs. Is this lone pair allylic? It's not, because if you go one atom over, it's not an atom in a double bond. So it's not allylic. Are these lone pairs allylic? They're not, because they're on an atom in a double bond. They're not one atom away from an atom in a double bond. Are these electrons allylic? They're not, because they're on an atom in a double bond. They're not one atom away from an electron, from an atom in a double bond. Are these electrons allylic? They are, because they're one atom away. If you go one atom over, you're at an atom in a double bond. So those are our allylic electrons, and because we have an allylic lone pair, we know that we have resonance, so we want to warn the world. We warn the world by drawing in those huge brackets that tell people, watch out. These structures, even though we took the time to draw them, neither of them is true. The truth is the average between them. So remember that when you have an allylic lone pair, the curved arrow pattern for that is the allylic lone pair always goes toward the bond that connects it to the double bond. And the pi electrons in the double bond always go onto the atom in the double bond that's further away from the allylic lone pair. So to draw that other resonance structure, first let's copy the one we have. And now, let's circle the atoms the electrons are moving around, because those atoms might have a formal charge that changes. And if there's a carbon there, then we'll want to draw any hydrogens on it, because that'll help us calculate the formal charge later. We do have a carbon. The carbon doesn't have a formal charge in this structure, so it should have 4 bonds. 1, 2, 3, 4 are already drawn, so there are no hydrogens we have to worry about drawing on that carbon. Notice that any hydrogens on heteroatoms always have to be explicitly drawn in. If they're not drawn in, then they're not there, as in the case of these oxygens. All right, so let's look at those curved arrows. Wherever you have a tail of a curved arrow, those electrons are moving. And because they're moving away from there, you erase that. Wherever you have the head of a curved arrow, electrons are arriving there, so you want to draw electrons. If the head of a curved arrow is pointing at a bond, then you draw another bond. Wherever you have the tail of a curved arrow, those electrons are moving away from there, so you erase those electrons. Wherever you have the head of a curved arrow pointing, electrons are arriving there, and so you draw in electrons. If the head of the curved arrow is pointing at an atom, then you draw the electrons as a lone pair. So this is our other resonance structure. Now we just want to calculate the formal charges that might have changed. On this oxygen at the top, 6 minus, we have 6 dots. Around that oxygen there's just one line, 6 minus 7. That gives that oxygen a negative charge. This carbon, 4 minus 0 dots around that carbon, 4 lines, and so that has a 0 formal charge. This oxygen, group 6A, minus 2 dots and 3 lines around the oxygen, so 6 minus 5, 6 minus 5, that's a positive 1. And so that oxygen is going to have a positive 1 charge. And so this is 5-amino 4-oxopentanoic acid. This drug used in hepatic tumors. The true drug doesn't have a double bond here or a single bond. It's something in between. And it doesn't have a single bond here or a double bond, something in between. And the charges are not full charges. They're also not 0 charges. There's something in between. And the significance of this is that this molecule, because it has resonance, it is stable, more stable, and it's also more rigid. And those are things that make it a good chemical messenger, or in other words, a medicine.